8,500 RPM. That's where Bill Jenkins made his Powerglide transmission shift in 1975. To put that in perspective, most street automatics blow up before they hit 6,000 RPM. Factory engineers at Chevrolet designed the Powerglide to shift at a conservative 5,500 RPM maximum. Yet here was this Ohio racer, deliberately forcing his transmission to hold each gear until the tachometer needle was buried deep in what everyone else considered the danger zone. The result? He was walking away from competitors who had more horsepower, better tires, and bigger budgets, all because he understood something about transmissions that even the engineers who designed them had missed. Picture this. It's a humid Saturday night at National Trail Raceway outside Columbus, Ohio. The air is thick with tire smoke and racing fuel. In the staging lanes, million-dollar race teams are making final adjustments to their pro stock machines. These aren't street cars with racing stripes. These are purpose-built quarter-mile weapons producing north of 800 horsepower from naturally aspirated small blocks. Every component has been massaged, machined, and modified to within an inch of its life. Yet when the Christmas tree drops and these mechanical monsters launch down the track, one Vega keeps pulling away from the pack. Not because it has more power, not because it's lighter, but because its transmission is doing something that shouldn't be possible. Bill Jenkins wasn't just another weekend warrior with a fast car. This was Grumpy Jenkins, the man who'd already revolutionized pro stock racing with his scientific approach to engine development. While other racers relied on gut feelings and old-timer wisdom, Jenkins approached drag racing like a physicist studying particle acceleration. He had notebooks filled with equations, dyno charts wallpapering his shop, and a mind that could calculate gear ratios faster than most people could read them. But his greatest innovation wasn't in the engine compartment. It was in a transmission that General Motors had introduced in 1950 as a simple, reliable automatic for grocery getters and Sunday drivers. The Powerglide was Chevrolet's answer to the complexity problem. In an era when other manufacturers were developing sophisticated multi-speed automatics with elaborate valve bodies and Byzantine hydraulic circuits, Chevy took a different approach. They built a two-speed automatic so simple that a trained monkey could rebuild it. The Powerglide had just two forward gears, low and high. No intermediate bands. No complex planetary arrangements. Just a torque converter, a simple planetary gear set, and a few clutches and bands. It was bulletproof because there wasn't much to break. Chevy marketed it as the transmission for people who wanted to forget about shifting altogether. But here's the thing about simple designs. They're easier to understand. And when you understand something completely, you can push it places its creators never imagined. That's exactly what Jenkins did. While Chevrolet engineers saw the Powerglide as a convenience feature for suburban commuters, Jenkins saw it as a blank canvas for speed. The transmission's simplicity meant fewer parasitic losses. Fewer gears meant less time-wasted shifting. And most importantly, its robust design meant it could handle modifications that would grenade other transmissions. The conventional wisdom in 1975 was clear. You shifted when the engine started falling off its power peak, usually around 6,500 RPM for a built small block. Go higher, and you're just making noise, not power. The engine's power curve drops off, valve float becomes a real danger, and you're putting unnecessary stress on every rotating component. Every racing manual, every experienced crew chief, every magazine article said the same thing. Find your power peak, shift slightly after it, and let the next gear take over. It was gospel. It was proven. It was wrong. Jenkins had spent hundreds of hours on the engine dyno, not just testing peak power, but studying exactly how power fell off after peak. What he discovered challenged everything racers thought they knew about shift points. Yes, power dropped after peak, but it didn't fall off a cliff. A properly built race engine might make 820 horsepower at 7,200 RPM, then only 780 horsepower at 8,500 RPM. That's a 40 horsepower loss. Sounds bad, right? But Jenkins did the math that everyone else was too lazy to do. Here's where it gets interesting. When you shift from first to second in a Powerglide, your engine RPM drops dramatically. The gear ratio changes severe, from 1.76.1 to 1.00.1. If you shift at 6,500 RPM, the engine drops to about 3,700 RPM in second gear. Now you're way below peak power, maybe making 550 horsepower while you crawl back up the power curve. But if you hold first gear to 8,500 RPM, even though you're past peak power, you shift into second at around 4,800 RPM. That puts you much closer to peak power immediately after the shift. You might be making 700 horsepower instead of 550. Jenkins understood that drag racing isn't about peak power. It's about average power over the entire run. Every millisecond you spend below peak power is time your competitor is using to pull ahead. By shifting at what seemed like an insanely high RPM, Jenkins kept his average power higher throughout the quarter mile. It was brilliant. It was also completely contrary to what everyone knew was right. But understanding the theory was only half the battle. The Powerglide wasn't designed to shift at 8,500 RPM. Hell, it wasn't even designed to see 8,500 RPM. Making it work required complete re-engineering of the transmission's hydraulic system. Jenkins started with the valve body, the transmission's brain. The factory valve body used precise hydraulic passages and spring pressures to determine shift points. These passages were sized for street driving, where smooth, comfortable shifts were more important than speed. Jenkins machined new passages, increasing their size to flow more fluid faster. He installed stiffer springs that required higher pressures to compress, effectively raising the shift point ceiling. The clutch packs were next. Factory Powerglide clutches were designed for 100,000 miles of gentle suburban driving. They used organic friction materials that provided smooth engagement but couldn't handle the violent loading of an 8,500 RPM shift. Jenkins replaced them with sintered metallic clutches, the same technology used in aircraft brakes. These clutches could handle temperatures that would vaporize stock materials. They bit harder, engaged faster, and could take the punishment of repeated high RPM shifts without glazing or burning. The band adjustment was critical. The Powerglide uses a band to hold the planetary carrier during low gear operation. This band has to release instantly and completely during the shift to high gear. At 8,500 RPM, there's no margin for error. If the band drags even slightly, it creates heat and slows the shift. Too loose, and low gear won't hold under power. Jenkins developed a proprietary adjustment procedure, measuring clearances to thousandths of an inch and testing release timing on a special fixture he built himself. Line pressure had to be increased dramatically. Stock pressure was about 90 psi. Jenkins cranked it up to 200 psi. This required a modified pump, stronger pressure regulator springs, and reinforced case passages. The higher pressure meant faster, firmer shifts, but it also meant everything in the transmission was under more stress. Every seal, every gasket, every bearing was operating beyond its design limits. Lesser builders would have created a bomb. Jenkins created a precision instrument. The torque converter needed complete rethinking. Stock converters were designed for smooth operation from idle to highway speeds. They used fluid coupling to multiply torque at low speeds, then locked up gradually as speed increased. Jenkins needed a converter that would flash to high RPM instantly, then couple efficiently without excessive slippage. He worked with specialized converter shops to develop custom units with modified stator angles, different fin counts, and precisely calibrated clearances. These converters were so specialized they would barely work in street applications, but on the track they were perfect. Testing was where Jenkins separated himself from backyard mechanics. He didn't just bolt in his modified transmission and hope for the best. He had a transmission dyno in his shop, a piece of equipment most race teams couldn't afford or didn't think they needed. Every modification was tested, measured, and documented. He could measure shift timing down to milliseconds, record pressure traces during shifts, and monitor temperature at multiple points. When something failed, and things failed constantly during development, he knew exactly why. The first time Jenkins showed up at a race with his high RPM Powerglide, competitors thought he'd lost his mind. They could hear his engine screaming past what sounded like reasonable shift points. Veteran racers shook their heads, expecting to see aluminum shrapnel and transmission fluid decorating the track. But run after run, Jenkins' Vega kept winning. Not by a little, but by car lengths. The timing slips didn't lie. His 60-foot times were comparable to everyone else's. His mile per hour wasn't significantly higher, but his elapsed times were consistently lower. The racing community's reaction was predictable. First, denial. Jenkins must have a bigger engine, hidden nitrous, or some other illegal advantage. Tech inspectors tore his car apart after wins, finding nothing but a legal small block and that weird Powerglide. Then came the excuses. He was getting better traction, favorable lane conditions, or just getting lucky. But as the wins piled up, excuses became harder to maintain. Finally, acceptance, followed immediately by imitation. Within 6 months, every serious pro stock team was experimenting with high RPM shift points. Transmission builders who'd been in business for decades had to relearn their craft. Parts manufacturers scrambled to develop components that could handle the new demands. What started as one man's weird idea became the new standard. But here's the kicker. Most teams could copy what Jenkins did, but they couldn't replicate his success. They had the same modifications, the same shift points, but not the same understanding. Jenkins knew that the high RPM Powerglide was just one part of a complex system. The engine had to be built to survive and make power at those speeds. This meant stronger valve springs, titanium valves, better rod bolts, and precisely balanced rotating assemblies. The cooling system needed upgrading because high RPM operation generated more heat. The oiling system required modification to maintain pressure and flow at speeds it was never designed to see. Every component had to work in harmony, or the whole system would fail catastrophically. The camshaft profile was crucial. Stock cams, even race cams of that era, were designed for peak power in the 6,000 to 7,000 RPM range. Jenkins worked with cam grinders to develop profiles that would carry power to 8,500 RPM without excessive valve float. These cams had more lift, longer duration, and steeper ramps than anything being run at the time. They made the engine practically undrivable below 3,000 RPM, but Jenkins wasn't building a streetcar. Valve springs became a science project. At 8,500 RPM, the valves are opening and closing 71 times per second. The springs have to be strong enough to control the valves at those speeds, but not so strong they wear out the cam lobes or break the valve stems. Jenkins tested dozens of spring combinations, measuring installed height, seat pressure, and open pressure. He discovered that dual springs with dampers worked better than single springs, and that spring temperature was as important as spring pressure. The bottom end needed bulletproofing. Stock connecting rods would turn into pretzels at 8,500 RPM. Jenkins used aftermarket forged steel rods, shot-peened for stress relief, and sized to exact tolerances. The pistons were custom-forged aluminum, designed to handle the increased cylinder pressures and temperatures. The crankshaft was a work of art, knife-edged for reduced windage, cross-drilled for better oiling, and balanced to perfection. But perhaps the most impressive aspect of Jenkins's innovation was his understanding of the complete vehicle dynamics. He realized that keeping the engine in its power band wasn't just about the transmission. It was about gear ratios, tire diameter, and aerodynamics. He calculated exactly what rear gear ratio would optimize the relationship between engine RPM and vehicle speed. He chose tire diameters that would grow predictably under acceleration, effectively changing the final drive ratio as speed increased. He even modified his car's aerodynamics to reduce drag at speeds where the high RPM advantage was greatest. The data acquisition was primitive by today's standards, but revolutionary for 1975. Jenkins had strain gauges on the drive shaft to measure torque, pressure transducers in the transmission to monitor shift quality, and thermocouples everywhere to track temperatures. He recorded everything on paper charts that he would study for hours after each race. While other racers were drinking beer and telling stories, Jenkins was analyzing data and planning modifications. The impact on pro stock racing was immediate and permanent. Within 2 years, the 8,500 RPM shift point became the minimum for competitive teams. Some pushed even higher, approaching 9,000 RPM. Transmission builders who couldn't adapt went out of business. New companies emerged, specializing in high RPM modifications. The aftermarket exploded with parts designed specifically for these applications. Jenkins had literally changed an entire industry with one weird idea. Chevrolet's reaction was interesting. Officially, they maintained that operating the Powerglide beyond design specifications voided any warranty and was not recommended. Unofficially, their engineers were fascinated. Several Chevy engineers visited Jenkins's shop ostensibly for routine technical support, but really to understand what he'd discovered. The knowledge gained from racing applications would eventually influence the design of future performance transmissions. The safety implications were serious. An 8,500 RPM transmission failure isn't just expensive, it's potentially deadly. The energy stored in rotating components at those speeds is enormous. When things let go, and they did let go, the results were spectacular. Explosions that would lift the front of the car off the ground, transmissions that would literally saw through the floorboards. Drivers needed additional safety equipment, including ballistic blankets around the transmission and stronger firewalls. Jenkins developed strict maintenance schedules that seemed obsessive to outsiders, but were necessary for survival. Complete transmission teardown and inspection every 20 runs. Clutch pack replacement every 50 runs, valve body cleaning and calibration every 10 runs. The cost was staggering. A single season of racing could consume a dozen transmissions worth of parts. But for teams chasing championships, it was a necessary expense. The psychological warfare aspect was real too. When competitors heard Jenkins's engine screaming past 8,000 RPM, still pulling hard in first gear while they were already in second, it was demoralizing. They knew they were about to lose before the race was over. Some teams tried to match his shift points without understanding the complete package, resulting in spectacular and expensive failures that further reinforced Jenkins' reputation as a mechanical genius operating on a different level. The evolution continued through the late 70s. As engines became more powerful and sophisticated, transmission technology had to keep pace. Jenkins pioneered the use of trans brakes, allowing drivers to load the converter against the transmission for more violent launches. He experimented with different fluid types, finding that synthetic fluids could handle higher temperatures and provide more consistent shifts. He even developed custom shifter mechanisms that could initiate shifts faster than humanly possible. The broader implications for motorsports were significant. Jenkins had proven that conventional wisdom wasn't always wise, that factory specifications were just starting points, that understanding the science behind the machinery was more important than following established rules. His approach influenced not just drag racing, but all forms of motorsports. Road racers started holding gears longer. NASCAR teams began experimenting with shift points. Even Formula One teams took notice of what a guy from Ohio had discovered about keeping engines in their power band. The legacy of the 8,500 RPM Powerglide extends far beyond drag racing. It demonstrated that innovation doesn't always come from major manufacturers with huge R&D budgets. Sometimes it comes from one person willing to question assumptions and test boundaries. Jenkins showed that complex problems don't always need complex solutions. The Powerglide was successful precisely because it was simple enough to understand and modify. Modern 8, 9, and 10-speed automatics might be technological marvels, but they're so complex that fundamental innovations are nearly impossible for independent builders. Today's pro stock cars shift at RPMs that would have seemed like science fiction in 1975. 10,000 RPM shifts are common. Some teams push even higher. The transmissions are still based on the Powerglide design, though they share little with the original beyond the basic architecture. They're hand-built masterpieces costing more than most people's cars. Every component is custom, every specification pushed to the absolute limit of material science. The lesson from Jenkins' innovation isn't just about transmissions or racing, it's about the power of questioning accepted wisdom. Every industry, every field of study, every aspect of life has its own version of the 6,500 RPM shift point. Rules that everyone follows because that's how it's always been done. Jenkins proved that sometimes the biggest advantage comes not from having more resources, but from being willing to think differently about the resources you have. Modern transmission technology has obviously evolved far beyond what Jenkins pioneered. Today's performance automatics use computer controls, advanced materials, and sophisticated engineering that would seem like magic to 1975 racers. But the fundamental principle Jenkins discovered remains unchanged. Keep the engine where it makes power. It sounds simple because it is simple, but it took someone willing to ignore what everyone knew to be true to prove it. The Powerglide itself is now largely obsolete in professional racing, replaced by purpose-built racing transmissions. But in sportsman classes, in bracket racing, and among weekend warriors, modified Powerglides based on Jenkins' principles are still winning races. Transmission shops across the country still use techniques Jenkins developed. His notebooks, filled with calculations and observations, are studied like religious texts by aspiring transmission builders. What made Jenkins truly special wasn't just his willingness to experiment. Lots of racers try crazy things. What separated Jenkins was his methodical approach to innovation. He didn't just guess that 8,500 RPM might work better. He calculated it, tested it, refined it, and proved it. He turned intuition into science, and science into winning. In a sport where success is measured in thousandths of seconds, Jenkins found seconds. The human element of this story is often overlooked. Jenkins wasn't a corporate engineer with unlimited resources. He was a racer, trying to win with what he had. The Powerglide modification came about not because he wanted to revolutionize racing, but because he needed an edge over better-funded competitors. Necessity, as they say, is the mother of invention. Jenkins' necessity was beating teams with bigger budgets, and his invention changed the sport forever. The technical challenges he overcame seem almost quaint by today's standards. Modern racers have access to computer simulations, advanced metallurgy, and precision manufacturing that Jenkins could only dream of. But that makes his achievement more impressive, not less. He did it with slide rules and intuition, with trial and error, with parts modified on manual machines in a small Ohio shop. He proved that innovation isn't about having the best tools, it's about understanding the problem better than anyone else. The 8,500 RPM Powerglide also represents something uniquely American about hot rodding and racing. It's the spirit of taking something ordinary and making it extraordinary, of pushing boundaries not because it's safe or sensible, but because it's possible. Jenkins embodied that spirit, and his transmission modification became a symbol of American racing ingenuity. It showed the world that innovation could come from anywhere, from anyone willing to question the status quo. As we look back nearly 50 years later, Jenkins's innovation seems obvious. Of course, you should keep the engine in its power band. Of course, you should shift at the RPM that produces the best average power. But that's the nature of revolutionary ideas. They seem obvious only after someone proves they work. Before Jenkins, shifting at 8,500 RPM wasn't obvious. It was insane. It took courage, intelligence, and a deep understanding of mechanical principles to turn insanity into innovation. The story of Bill Jenkins and his weird Powerglide is ultimately a story about the power of understanding. Not just understanding how things work, but understanding why they work that way and whether they could work better. It's about the difference between knowledge and wisdom, between following instructions and writing new ones. Jenkins didn't just operate transmissions, he understood them. And that understanding changed everything. Today, when young racers ask about finding an edge, old-timers tell them about Jenkins, about how one man with a different idea beat teams with every advantage, about how questioning conventional wisdom led to conventional victory, about how sometimes the best modification isn't adding something new, but using something old in a new way. The 8,500 RPM Powerglide isn't just a piece of racing history. It's a reminder that innovation is always possible, that accepted wisdom should always be questioned, and that sometimes weird ideas are the best ideas. So what's your 8,500 RPM shift point? What accepted wisdom in your field might be holding you back? What rule that everyone follows might actually be wrong? Jenkins proved that breakthrough innovations don't always come from breakthrough technology. Sometimes they come from breakthrough thinking. And that's a lesson that applies far beyond the drag strip. What's the most unconventional modification you've seen actually work? Drop a comment below and share your own story of mechanical innovation. And if you enjoyed this deep dive into racing history and the engineering that changed the sport, make sure to subscribe. We're just getting started exploring the machines and minds that push the boundaries of what's possible.